So welcome back, everyone, to those of you who have been to the previous webinars, and welcome to those of you that haven't. This is the third webinar in our 6-part webinar series called Discover Anemoi, in which we outline the main components of the anemoi ecosystem. So today's webinar is presented by Mario, who I'll hand you over to in just a minute, and it's on anemoi-graphs. The previous 2 webinars we had last week were on an introductory webinar, and then one on data sets. And then on Thursday, we'll have another webinar on training. And then next week, there'll be 2 webinars, one on inference and one on developers. So you can see those dates there on the top right. And if you scan the QR code, that'll take you to the event page where you will surely have been to get to this webinar. And you can register for those webinars. Unfortunately, we have to register individually for each webinar, so I apologize if that's a bit of hassle, but hopefully not too much. Don't forget that webinars all start at 3 o'clock Central European Time or 2 o'clock UTC. And as always, the questions, if you have questions, you can ask the questions in the chat, and we will try to answer those directly in the chat as we go along. And then we will have time at the end of the presentation for a few more questions, in terms of discussion. So the presentation should last around 35 to 40 minutes, something like that. And the last thing to say is that the webinar will be recorded, as the others have been. And if you now go to our event page, you can find this section on the left menu called Webinar Recordings. And we have already the previous 2 webinars there, which are on YouTube, and we have the links there in the slides. And this webinar will, of course, be recorded and put there as well. So that's all there is to say, and I will now hand you over to Mario to talk about anemoi-graphs.
Thank you, Will. So first of all, welcome everybody. Let me introduce myself. My name is Mario Santa Cruz, and I am part of the team developing anemoi and AIFS here at the ECMWF. And today I will be introducing you, as William said, the anemoi-graphs. So just coming back to anemoi, what it is anemoi? Anemoi is an open source framework developed by the ECMWF and also other national med services to develop machine learning weather forecasting models. It is a framework because it contains different Python packages for data preparation tools, graph creation tools, for training your machine learning model, for doing the inference, and also for registering your dataset or your training models. Why the user should use anemoi? Because there are like a lot of common meteorological challenges that have already been solved by anemoi, and you as an user can bring your data and you can start training your models using existing recipes. So these are like the main benefits of using anemoi. Here in the right, we have like the diagram of dependencies of the different Python packages, and we can see here how the main entry point that it is like training, anemoi training, we want to train a data-driven weather forecast model, has 3 arrows pointing to the models, datasets, and graph. These 3 things are the 3 main components that we need to train a model in anemoi. The dataset, that it is produced with anemoi dataset, the graph, that it is produced by anemoi graphs, and then the model that it is produced with anemoi models. The dataset is just a SAR dataset, as you may know, the ones who attended the last webinar. The graph is just a PyTorch geometric graph, and then the model is a PyTorch model. So let's go a little bit in detail into these 3 components, starting just with a recap of the previous webinar. Anemoi datasets is the tool we use for creating these datasets. That the idea here is just to make a copy of the dataset that it is ready for machine learning training. What we want when training a machine learning model is that the training is fast. So to make the loading of data samples as efficient as possible, we have to minimize the number of I/O operations. And to this aim, SAR is the best option we found because of its chunking. In our particular case, we use each file, like we chunk the dataset in files corresponding to single dates. In the left part of the slide, you have the documentation page of the anemoi dataset. You can check there more in detail documentation. And you also have the shape of the dataset that we will have. So dates, variable, ensemble, and the last dimension will be the grid points. One important thing just to point out is that we don't have two dimensions for the spatial dimensions. We just have one that it corresponds to the whole grid points. And one of the main benefits of using anemoi datasets is that it supports more complex operations when using several datasets. So, for example, it supports subsetting datasets based on time, variable, or ensemble member. And it also supports combining multiple datasets using operations like join, concat, or other more complex as the catalog one. Then the second component that anemoi needs for training a model is the graph that will the main part of this webinar. And a graph is just a tuple of nodes and edges where the nodes represents locations in the earth in this case. And the edges are just the connections between these nodes who will define how the information flows during the model. This graph is represented by heterodata. It's a specific class of torsiometric library, and it can be stored in our local file system as a .pt file. In the right part, we can see how is this, what shape does this object, the shape of this object. It contains the nodes and the edges. The nodes are represented by 2D matrices which contain the coordinates of the nodes. For the edges, it is again represented by 2D matrices, in this case of integers representing the indices of the source and target nodes for each edge. And then the last component is the model. If you keep coming to the webinar series, you will get more details on this in the next webinars. But just to introduce to you, in anemoi, we rely on graph neural networks (GNNs) that are a specific type of neural networks that works with graphs. This means that the input and output of the model is a graph. And in this context, we use an algorithm named message passaging to propagate the information from the network. This algorithm has three main steps. It starts creating a message based on the node and edge features. Then it aggregates that message based on the connectivity, on the graph connectivity, and the last step is just update the node values. Here I also included the documentation for the anemoi-models package. So now that we have gone to the three main components, we can just get more into depth into the one that it is interesting for us today, that is the graphs. And for the graphs, we have the anemoi graph that it is, as mentioned before, the specific Python package that help us create those graphs. In particularly, for creating those graphs, we are using YAML files. These are the recipe that define how we want to build the graph. In these recipe files, we will have to define both the nodes and the edges. And in addition, we can also include information about attributes for both the nodes and edges. So now is how can we run anemoi graphs? For this, we have the command line tool that provides with three main entry points that are described here. The first one is just create the graph. You can write in your console anemoi graphs create recipe YAML, .yaml, and then the output graph file. That will create the file. And once you have your file in your local system, you can describe that specific graph using anemoi-graph describes, or you can even inspect visually the graph. In this case, we also have to add an extra argument, in this case graph bis, that corresponds to an output folder. In this folder, we will write some plots. Some of these will be static plots corresponding to the distribution of some features, but we also have HTML files. These HTML files are interactive plots for debugging the graph connectivity. One important disclaimer here is that these inspection tools, like the HTML files, are provided for medium size and small size graphs. So be aware of this when you try to run high resolution graph, the inspection tools with high resolution graphs, as these HTML files might not load. So once we have, now that we have, that we know how to use anemoi graphs, we have to understand what is the graph. And here in anemoi, particularly in anemoi train, we use always a specific type of graph structure. For those who have experience with machine learning and deep learning, there is a very famous architecture that is the UNet. So this is very similar, the encoder processor decoder graph structure. And as we mentioned, the graph is just nodes and edges, right? So let's start with the nodes. In anemoi training, we will have two main sets of nodes, the data nodes and the hidden nodes. The data nodes will represent the locations of the input and output data points. And then the hidden nodes are set by the user, usually at a coarser resolution than the data nodes. This allow for the model to extract some features and do the dimensionality reduction. This will be the bottleneck in the UNet shape. So now, first of all, take a look, please, to the diagram in the right. Here we can see the UNet shape mentioned before. As we mentioned, the hidden will have a coarser resolution than the data. We have defined our two sets of nodes, the data nodes and the hidden nodes. And once we have defined these two sets of nodes, we can define the three sets of edges. The encoder edges, those coming from the data to the hidden, then the processor edges, and then the decoder edges. So that's the graph. And now let's go back to the recipe in the left. You can see that there are two main blocks corresponding to the two main components of the graph, the nodes and the edges. Let's start looking at the nodes. In this case, we have defined two nodes, two sets of nodes, the data and the hidden nodes. These are the names we have decided, but you could decide to use other names for those nodes. Following the node name, we have to specify the node builder, that it is just a specific anemoi graphs class. You could also extend this with your own classes. For the edges, is very similar, with the difference that for each encoder, processor, or decoder, you have to specify the name of the source and target nodes. As you can see here, for example, in the encoder, it's just the edges going from data to hidden. And once you have defined which are the source and target nodes, you can define the edge builder. And similar to before, these are anemoi graph classes. Okay, so now let's go with more in detail to this recipe file. For the nodes, we start with the data nodes. This is the easiest one, as we always want the data nodes to match our training dataset. So in this case, we always want these data nodes to be SAR dataset nodes and just equal to our training dataset, right? And now move to the hidden nodes. You have in the top right of the slide the part of the recipe that refers to these hidden nodes. And here we are using a tree nodes class. What does it mean? These names come for triangular refined mesh. What it means is that we are creating an icosahedron projected to an sphere, where each face of the icosahedron corresponds to one node. And we can refine this icosahedron as many times as we want. In each of these refinements, we increase the number of nodes by 4. Here, as you can see back into the recipe, this resolution parameter in this case matches the number of refinements we want to apply. One important property of this class is that the nodes at one refinement, so the dot in the blue triangle, are also nodes in the next refinement. So this dot in the blue triangle is also part of the nodes in the orange triangles. Okay, so now we have defined both the data nodes and the hidden nodes. It's time for creating the edges, and we start with the encoder. In particularly here, we have decided to use the cutoff edges. That is it is not the only option, but it is a very common one for the encoder. Very easy to understand. Look at the diagram on the left. The black circles are the target nodes, and the blue circles are the source node. So what we are doing with this method is to define a circle around each target node, and we will connect all source nodes inside that circle with that corresponding target node. Okay, so this radius is defined based on the cutoff factor. You can check the documentation to see how this is computed. And here there is an important trade-off to be aware. On one hand, we want to minimize the number of edges just for efficiency. The smaller the graph, the less edges we have, the smaller the graph, and the more efficient it will be just to run one forward pass. So the cheaper it is in inference and the faster we train. Okay, but on the other hand, we want to maximize the information flowing to the hidden nodes. Why is this important? Because if we don't connect a source node, a data node to the hidden nodes, the information in that data node will not be used at all by the model. Okay, so just to be aware of this trade-off here. Then we have the processor, and for the processor, we have specified here the multi-scale edges. This is a type of edge builder that can only be used when the hidden nodes are built with the tree nodes. Remember this tree refined mess. So these multi-scale edges are can only be used with these tree nodes. And why? It is because we rely on these refinements to define what it is a neighbor. A neighbor will be two nodes will be neighbors if their corresponding faces are one next to the other, right? And you may be asking yourself, why multi-scale? It is multi-scale because we do these connections at all refinement levels, not only in the last one. So now you can see that we have connections like small scale connections and large scale connections. The large scale connections can go across continents even. Those will correspond to the connections made at refinement 0 or 1. And lastly, we have the decoder that here is very common to use the nearest neighbor edges class, and this just selects the nearest neighbors for each target node. Just as a note, this will be the part of the graph with more edges in most of the time. Here we'll have around 3 or 4 times the number of data nodes compared to the encoder, where usually we have like around the same number of edges as data nodes. Okay, so now we have explained the encoder processor decoder configuration, the most basic one. But there are also other options that are supported in anemoi-graphs. So for example, the hierarchical processor. This is a specific type in which we can include more hidden nodes levels. This is very easy, just adding one more set of nodes in the recipe and the corresponding extra encoder and decoder edges. So those going from hidden 1 to hidden 2 and from hidden 2 to hidden 1, right? And similar with the multi-encoder and multi-decoder. It is as easy as in the recipe file adding one more data nodes and the corresponding set of edges going to the hidden, right? But with any of these type of graphs, we can be interested in different use cases. Some users may be interested in global graphs like us, ECMWF, when training our AIFS. But other users may be interested in specific regions. In that case, anemoi offers two options, the stretch graph and the limited area graphs. The main difference here is that the stretch graphs has a coarser resolution. The stretch graph has a coarser resolution outside the in all area outside the region of interest. And the limited area graph, it only contains a small boundary around the region of interest. Okay, so now let's see how the recipe change when we want to focus on a limited area setup or in a stretch grid setup. First, the data is staying the same. We are just pointing to our training dataset. In this case, the training dataset will be slightly different as we normally combine two datasets with the cutout operation. But for this, if you don't understand this, you probably need to check the webinar series, the video on the webinar on anemoi dataset to understand this cutout operation. But this supports to pass the configuration directly to anemoi datasets to read both datasets together. And we have here one thing that we didn't see before, that it is the attributes that were mentioned during the presentation today, but we didn't see those in the recipe yet. So it is just an optional field added to the nodes where we can define as many attributes as we want. In this case, we define two, area weights and cutout mask. Area weights will just assign the area corresponding to each node. This is usually used for as a weight in the loss function. And then we have the cutout mask. This cutout mask will be used, will tell us if a node is part of the region of interest or not. So if it is part of the first dataset or from the second dataset, okay? So the data nodes are built the same for both cases, the limited area and the stretch graph. Now the difference is in the hidden. In case of the LAM, we will be using limited area tree nodes, very similar to the class we mentioned before that it was tree nodes. In this case, it's limited area tree nodes. Similar as before, we specify the resolution argument. This is the number of refinements of this triangular, of this icosahedron, right? And then we have two new arguments. These are the reference node name and the node attribute name. These attributes, these arguments are used by the node builder to know what is the region of interest. So basically what we are reading from this configuration is, build me the three nodes, please, only in the area with data nodes whose cutout mask is equal to true, okay? And this is the result in the right. You can check the plot where the dots correspond to the data points, the data nodes, and the circles that are only here around Europe. This is more or less Serra reanalysis. So the circles correspond to the hidden nodes that are only defined in the region of interest. For the stretch grid, in contrast, we can see that now we have hidden nodes also. We have data nodes in the same exact locations as before, but now the hidden nodes, the circles, are in both the region of interest but also outside. And how can we create this set of hidden nodes? Similar as before, but we have to change the class we use. In this case, we use a stretched tree nodes. And similar as before, we use reference node name and node attribute name to specify the region of interest. So data nodes, and from those data nodes, use the ones that have cutoff mask equal to true. And then the resolution argument is now split in two arguments that specify the resolution inside the area of interest and outside the area of interest, right? Okay. And once we have defined the data and the hidden nodes, we can use the same configuration as before. This will be valid for both the limited area and the stretch graph, right? And as before, here we are adding the attributes argument. So we define the source name, the target name, the edge builder, and then it is optional to define the attributes, which may contain also as many attributes as you want. First the name and then the class with its arguments. In this case, we are only use edge length, but you could use more like the direction of the edge or others. Just check the documentation for more information about this. And then just as a final slide, a quick wrap up of anemoi-graphs. First of all, is just to be aware that you don't need to use anemoi-graph at the beginning, as it will be used by anemoi training to create the graphs on the fly. And this is possible because you already have a lot of these recipes for global graphs, for limited area graphs, for stretch graphs. You have these recipes in anemoi training. So you don't have to worry in anemoi-graphs for anemoi-graphs in the beginning. Also, be aware that if you want to use anemoi-graphs, you have a command line tool to create and inspect these graphs. Also, be aware that anemoi-graphs is designed to be extended with new code. So you, the user, may create new node, edge, or attributes builder and instantiate them directly in the recipe. Also, it's important just for you to know all of the use cases supported in anemoi-graphs. So the global graphs, the regional graphs like limited area and stretch, but also more complex setups are possible, like the multi-encoder and decoder dynamic graphs, which are supported in anemoi-graphs, but they are not yet, there is no use case at the moment in anemoi training that support, like, for example, multi-encoder or multi-decoder graphs, right? And then just as an important note, probably at the beginning, you don't need to tune a lot the graph because you will get to a reasonable good model. But when you want to get the best model possible, at that point you probably have to come back to the graph and tune the configuration, not just to make the best model in terms of accuracy, but also in terms of performance. Given that the smaller the graph, the more efficient it will be, the training, but also the inference. So with this, I finish. Thank you very much. You have the documentation there in that page. Now you can write any question. Thank you.
Thanks, Mario. That was really, really good. The chat has been quite quiet, but we do have a question, and maybe people might want to write a few more questions as we answer this one. Oh, by the way, if anyone wants to actually raise their hand and say something, in fact, there is also a hand up I see, but I'm going to go with the chat question first. So you may see this, Mario, but I'll read it out for everyone. It says, I'm curious, and this is from Clement. Do you have a rule of thumb to adjust the hidden nodes resolution to the data nodes resolution so as to avoid any subsampling aliasing effect, or to equalize the number of edges flowing to one given hidden node? Does this have an impact at all, e.g. on training?
One rule of thumb would be like use one fourth of the data nodes. So when we use 1 degree resolution in the data nodes. We use around 2 degrees in the 2 degree resolution in the hidden nodes. So that would be like the rule of thumb that we are more or less following.
Okay, so there was someone with their hand up, but it looks like it's gone back down. But there's two more questions in the chat. So the next one is, are there plans to add support for multi-encoder or dynamic graph setups? How easy would it be to extend the current code base for such a setup?
These are things that are already supported from the graphs perspective. So anemoi-graphs is a very general tool that you can build graphs for anemoi, but those graphs could also be used outside of anemoi if you have your own library. So this is already supported from the anemoi-graphs perspective. And from the anemoi as a framework, so anemoi training, there is currently some ongoing work in make this possible in a future, but there is a lot of work to be done by ECMWF and all the member states, all the national med services. It is something that we are working on.
Okay. Next question, and I'm keeping reading these out, so it will be recorded for the recording as well. So otherwise, it might not make much sense. So yeah, the next question is, the graph setup looks very flexible, but might also have a performance impact. Was it considered to allow longitude, latitude, plate carré? I'm actually not sure what that is. Setups like used by Fuchsi weather.
I don't know exactly what is the setup of the Fuchsi model, but yeah, anemoi-graph is quite flexible, and at the end, for defining the nodes, the only thing that we need is a set of latitudes and longitudes. So there are other classes where we can pass them directly these values. So based on a TXT file or in NumPy tensor. So this is quite easy to use for that case.
Okay. On to the next question. Could you comment a bit about the resolution of the graph? Does it depend on the resolution of the data, or you can tune the resolution of the graph independently of the data?
Okay, so the resolution of the graph, you cannot talk about the resolution of the graph. You may talk about the resolution of the nodes, or even if the nodes, it may be hard. In particular, the data nodes will have the same resolution as the dataset because these are the input data and output data, so it has to match the dataset. So the resolution of the data nodes will match the resolution of the dataset. For the hidden nodes, what we want is to have like a coarser resolution, just to have this dimensionality reduction, allow the model to learn also large scale patterns. So just that the data nodes resolutions is equal to the dataset resolutions, and then the hidden resolutions is lower than that, but the user can define that. The user could even define like a higher resolution, but the use case, I don't know if it makes a lot of sense.
Yeah, I think it makes sense. By the way, since we still have time, if anyone does want to raise their hand and ask a question on camera, we have the option is there. But in the meantime, I'll just read out. There's two more questions, maybe three now. So the next question is, would it be possible to have one stretched graph with several high resolution domains over the globe? For instance, the first one over Europe and the second one over the tropics, instead of a single high resolution domain?
Yes. In fact, this is possible. You can check the documentation, but the idea would be you still have the stretch graph over only with one area of interest, but now you can define that area of interest as the union of different regions. So what it is supporting now is to have this stretch graph with one coarser resolution, and then the high resolution in different places, so the Nordics and the Iberian Peninsula. But what it is not possible, but I know that there is also ongoing work on this, is just to have even different resolutions for each of those. So have a refinement level of 5 in the whole globe, 6 in the Nordics, and 7 in the Iberian Peninsula. That is not possible, but I know that there is ongoing work just to make it that happen.
Okay, so next question is, would it be possible to implement a graph that performs the same as a UNet network?
Should be, yeah. I mean, the graph is just a generalization of even a matrix. You could just take a matrix where each pixel is just a node and connect each node with their neighbors in the matrix. So this won't be as efficient as a 2D matrix, but in theory, this is just a generalization of a 2D convolutional.
Okay, so the next one is, can the set of data nodes be unstructured, e.g. not a gridded reanalysis in anemoi?
Yeah, sure. We are only relying on the SAR dataset. The SAR dataset has a latitude attribute and a longitude attribute, and we read from that. I mean, you could also, if anemoi dataset handles observations, you can also create the data nodes in the observation location. So that's not the problem. That's not a problem.
Okay, so there's two more questions. Is there any relation between the encoder and decoder? For example, do we have properties like a decoding step followed by encoding step is the identity operator? Not sure if that makes sense to you,
No.
Mario.
No. At the moment, the encoder and decoder are like two independent steps. In fact, the edges are not the same. I mean, it will be completely different. You have way more edges on the decoder than in the encoder. The idea in the encoder is just to shrink all the information to the hidden. So it would be fine if you have for each data node one edge, but in the other side for the decoder you want like for each data node you want all the surrounding information just to make the final prediction to decode the final state, and to that we generally use like 3 or 4 neighbors, so it has like around 4 times more edges the decoder than the encoder.
Okay, so I think this is the last question. It says, I'm sorry if my question is too naive. I don't think it is. I'm not an AI expert. You mentioned that the number of input nodes and output nodes may be different. Does it mean that, something just came up. Does it mean that I can use gridded data sets, e.g. IFS analyses as input and non-gridded data set, such as measuring stations as an output?
Yeah, you could use that. In this presentation, I always refer to data nodes because in the currently supported use case, input data nodes and output data nodes are the same, but it doesn't have to be that case. The case you were explaining is one example, but also downscaling. Downscaling should be feasible to have this in anemoi, and in that case, the input data nodes and data nodes, they are not like the same. So yeah. It wasn't like a naive question at all.
Okay, there is actually one more question, so we might as well take it since we still have time, if that's okay. So someone says, I'm a beginner and I'm trying to run anemoi for the first time. Do I need to create a graph before using the train function, or is it possible to create the graph by providing the dataset in the YAML config recipe?
So the fast answer would be like wait for Thursday webinar on anemoi training. But yeah, you don't need to create the graph yourself. In anemoi training, you have different recipes, graph recipes that you can use, and anemoi graphs will be used under the hood to create this graph. So don't worry about using anemoi graphs directly there.
Okay, so I think that is, I think we'll stop there because that's the end of the questions. That's a lot of questions, and Mario handled it very well. And so I'd like to start by or end by first of all thanking Mario for the fantastic presentation and answering all the questions. And thanks to all the people that asked the interesting questions, and of course to everyone who came along and listened. There is just a couple of very last things. We do have a very short survey, so you can see on the slide there's a QR code. If you do want to just leave any feedback for the webinar, it's 2 questions and the option to leave a comment if you want. So it's extremely quick, but it does help us to improve and direct our future training. So any comments are very welcome. You can also send us an email to this address here. And with that, I think we will close the webinar there. So thanks again to everyone and see you next time, hopefully on Thursday for the next webinar. Goodbye.